Okay, let's have some fun. Let's do some math with exponential functions. So check out this problem. This is a pretty common exponential growth type of problem, and although it talks about investing in money, which I hope is interesting to you, this problem could involve anything, and we'll look at some other problems, some other word problems that involve exponential growth and exponential decay. So anyways, in this case, it looks like the money's growing. We originally invest $1,800, $1,800, and the value increased by 7% each year. And we're supposed to write an exponential function to model the situation. Then find the value of the investment after 15 years. So we'll try to do both. And I have to say, I don't know if you've been watching or listening to the news, but there's been an awful lot of talk about mathematical modeling of the coronavirus. And all mathematical modeling means is coming up with an equation that explains what is happening with the data. In other words, in the case of coronavirus, how is it growing? How many new cases do we expect to get in a certain period of time? And you'll notice that this problem is very similar. We're looking at how many new dollars we're expecting to get in a certain period of time with a known growth rate of 7%. Now, sadly, that 7% growth rate is highly unrealistic. It's going to be very hard to get that kind of interest on an investment today, but who knows, maybe at some point in the future, and maybe depending on what kind of investment. So anyways, we're gonna practice with this. So first of all, we're gonna say, let's just play around with numbers before we do any algebra or I give you any formulas. We know that if we have $1,800, and if we believe that it increases 7% each year, that means that if I multiply 1,800 times 7%, which by the way, do you remember how to write 7% as a decimal? It's pretty important. See, pause the video and see if you can remember, and then see if we agree. Okay. I'm hopeful that you paused the video. I'm going to go ahead and write 7% as a decimal. I'm going to go ahead and write it as 0.07. I have to admit, writing that 0 in front of the decimal is kind of optional, and I think one reason to do it is just to make it more clear that there is a decimal point, before we go on. Anyways, 7% is written as 0.07. Remember, the first decimal place is for 1/10, and the second decimal place is for 1/100th, and percents are 1/100th of something. 1% is 1/100th of something. Okay, so anyways, so we'll multiply 1,800 times 0.07, but that does not give us how much we'll have in the bank at the end of the year. All this tells us is how much interest we will have made on the 1,800. So if we want to know how much we have in the bank at the end of the year, also known as the balance, then we'll say plus, that's the interest amount, plus the original 1,800. And sometimes people will write this 1,800 out in front and then add it to the interest rate. Either way, it's fine. Because of the commutative property of addition, we can add in either order and we'll get the same result. And we're going to write that this is the balance at the end of year one. I'm trying to think. Yeah, balance at the end of year one. I'm just going to write balance for now. We're going to play around. I'd like to work with this in a way that it makes sense. So if it's not making sense, we'll back up and we'll try something else. Now, the thing that's kind of a bummer is to figure out what the balance is going to be at the end of the second year. So at the end of the second year, we're going to have 1,800 times, I'm going to abbreviate 0.07 because there's going to be a lot of writing here, plus 1,800. Okay, we're going to have all this stuff at the end of the second year, but in addition to that, we're going to have 0.07, we're going to have 7% interest, and plus whatever the original amount was, which was 1,800 times, oops, let me get the parentheses in here, times 0.07 plus 1,800. Now, that's the balance at the end of the second year. And if I try to write the balance at the end of the third year, it's going to get kind of obnoxious. So hopefully you're already recognizing it'd be nice if we could make this easier. One of the reasons that we talk about factoring out the greatest common factor a long time ago is because it's a useful tool in making math more simple. So what I'm going to do is I'm going to go back to this original equation here. And let's see here. I'm going to go ahead and draw a line because what we're going to do next is kind of a repeat of what we previously did, not a continuation. I'm going to go ahead and factor out the GCF from these two terms. If I do that, I get 1800 times 0.07 plus 1. Okay, that's factoring out the GCF from this guy. This is known as a term, and this is a term. The definition of terms are things that are added together. Now, when I do that, I get a much more simple situation, and I can make it even a little more simple because it's really easy to add 1 plus 0.07. When I do, I get 1.07. And it turns out that that looks a bit like a formula that I presented in a previous video that explains what exponential functions are. We can write an exponential function like this: y equals a times 1 plus the rate of growth raised to the power of t. We'll see the power of t in a minute, but for right now we'll say a is the beginning amount, 1800. And then we add 1 to whatever the growth rate is, in this case 7%, and then we'll see why we have a t up here as an exponent in just a minute. So this is still the balance at the end of year 1. Let's take a look at the balance at the end of year 2. So again, all this stuff right here is simply this. So what's happening is, let's see here. I'm going to be multiplying. I'm going to take again. I have a GCF, and the GCF is kind of huge. My GCF is this. It's all this because look, I have the same thing written exactly right over here. All I'm doing that's new, if I take that GCF out, I just multiply the end of the first year balance times 0.07 plus 1. So again, so what I would end up doing is do something like 1800 times 1.07, and that would be my end of my first year balance, and I would multiply that times 0.07, all of that, and then I would add that to 1800 times 1.07. And that would be my end of my second year balance. But again, I still feel like I'm doing too much work. So I'm going to go ahead and factor out the GCF again. So again, this is not continuing. This is a repeat of this second line. All I'm doing is rewriting this. By the way, let me make it real clear that that's all this is. Okay, and so then I say let's factor out the GCF, which is going to be let's see here. Okay, so what we have is the GCF is 1800 times 1.07. So we get 1800 times 1.07. That's our GCF because it appears here and it appears here. And if we factor it out as a GCF, then what's left over is 0.07 plus 1. Also known as 1.07. So I'd like to point out that this becomes, and I'm going to change color now because now we're making some significant progress here, 1800 times 1.07 times 1.07. Now, this will be the balance at the end of the second year, okay? So you'll notice that there's two 1.07s. So another way I could write this is like this. 1800 times 1.07 raised to the power of 2. You'll remember that something times itself justifies the exponent of 2. Now, if we had 1.07 times 1.07 times 1.07, we'd put a 3 here. And it turns out that for the balance at the end of the third year, that's exactly what we'd have, is 1.07 times 1.07 times 1.07. So this is the balance at the end of year 2. This up here, let me make sure this is clear. This up here, this first line was balance year 1. end of year one technically. And down here, this is balance. And this will be for year two. Now, I've told you all this, and you've been very patient, and I've told you all this because I want it to make sense to you why this formula works the way that it does. To me, being able to use this formula is not nearly as good as understanding why it works and that it actually works. I want you to believe it works, and I'd like you to know how it works. And if you know all that stuff, then you'll be able to use a formula like this more consistently and more accurately. And it turns out formulas like this are used in the real world pretty commonly, like in problems like this. So in the end, let's go ahead and finish this off. For this problem, if I wanted to know the value of my the model would be something like this. Let's go ahead and write the model. Let me go ahead and clear off some of this writing so that I can give you the final result here. So okay, so the model that we are coming up with is that the balance at the end of any given year is going to be equal to the original amount, $1,800, and that'll be multiplied times 1 plus the interest rate, 0.07, and that'll be raised to the power of t, which is whatever the number of years is. And then let's go ahead and use this model. And by the way, when we do make a model, usually we'll have, and by the way, that t could be an x, so it's more familiar to us. That's fine. Basically, what we do is we change the value of x, and y is dependent on the value of x. X is the independent variable, y is the dependent variable. And we change the value of x, and we get different values of y. Different number of years give us different balances in our account. So let's go ahead and use that model to make a prediction for this situation when we were told 15 years. So we'll say the ending balance, let's see here, this will be y, will equal the starting amount, 1,800, and I'm going to abbreviate. This is times 1.07. 1 plus 0.07 is 1.07, and we'll raise it to the power of 15. Now, I have to admit, some people do get this wrong, so it might be nice for us to do this math together. But before I do, I would like to just make real clear, I'd like to define these things. This is the balance at the end, of 15 years. And by the way, the y in our model is basically the balance at the end of any number of years that we put in for t. Okay, balance at the end of 15 years. The 1,800 is the beginning amount. And by the way, that time does not always have to be in years. It just happens to be in years for this particular problem. That t could be seconds or milliseconds or nanoseconds, or it could even be decades. So it just depends on the context of our problem. Okay, let's go do the math. I'd like you to try to do the math, and then I'll do the math, and let's compare notes. Since we're trying to get dollars, we will round to 2 decimal places so that we'll have, cents at most. Let's see how this goes. Okay, so I'm going to share a couple tricks with you. First of all, to make it so to help my calculator get the correct answer, I did this part first. I raised 1.07 to the power of 15 first. See, PEMDAS says do exponents before multiplication, so I hope you did. So that got me 2.75 blah 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 blah. And then finally I took that number and multiplied it times 1,800. And I kept all the decimal places initially, but we're going to round. So the correct answer should be at the end of 15 years, we should have $4,966.26. Hopefully you agree with me that you round to 26 cents. Now, who cares about the 26 cents? We are happy that our $1,800 turned into $4,966. Now, you might say to yourself, $4,966 really isn't that much for 15 years. And I tend to agree with you, especially in this day and age. However, I will say this. I want to point something out. let's say that this was $1.8 million that you started with, and you invested it like this for 15 years. At the end of 15 years, it turns into $4.9 million. And that is the beauty of in a way, this is sort of compounded interest. It's just annually compounded interest. Okay, anyways, that is your lesson on exponential growth and exponential functions. I've got a problem for you to try, and you're going to use your knowledge from the introduction video and this video in order to solve the problem. Okay, so here's the one problem that you have to do for your homework. Only one. And you have to write it out, and then you have to take a picture of it and submit it to Google Classroom to show me that you did it. And I'd like to see all the work as much as you can. So I will make it a little easier for you though. Instead of 1.5%, which will make the math hard to do, you're going to make it 2%. That'll make it a little bit more like my example. And the other thing that's not entirely clear here is they don't tell us the number of years. They say in 2002 there was this many students, and they want to know, write the model and then find the number of students enrolled in 2014. Well, how many years is that? Some of you would say 2014 minus 2002, and I'd like to check and see if that's correct. So what we're going to do is we're going to put in, I'm going to pretend like 2002 is year 0. Because doing math with 2002 is tricky, and doing math with 0 is easy. And then just to make sure that I've got my count right, I'm going to go 2003, 2004, 2005, 2000, 2005, 2006, 2007. See, it seems like we're one behind. 2000 or more than one behind. That was 2007. Let's see, 2003, 4, 5, 6, 7, 2008, 2009, 2010, 2011, 2012, 2013, 2014. Aha, 12. Okay. I have to tell you from my experience, it's worth making sure that this actually works, that it is actually 12. So sometimes if you're off by 1, you get the entirely wrong answer. But it does look to me like we can use 12 as the number of years. So I'll go ahead and help you guys out with that. Number of years is equal to 12. Okay, you guys go do the work, write the model, then find the number of students in the year 2014. In our case, total number of years will equal 12. Okay, good luck.